You know, we're always trying to figure out what's really going on with data. But what happens when that data comes from the real world? It's messy, it's complicated, and it's definitely not a perfect lab experiment. So how do we find a clear answer when things are just not that simple? Well, let's dive in and see how it's done.
And that's really the big question, isn't it? When you can't run a perfect, controlled experiment, how do you find the truth? Think about it. Does a new medication actually save lives? Does a new policy really have the effect we think it does? We're going to explore a really powerful technique for answering exactly these kinds of questions.
Okay, so in a perfect world, we'd use what's called a randomized controlled trial, or an RCT. It's the absolute gold standard. You just randomly put people into a treatment group or control group, and, like magic, chance makes sure those two groups are basically identical, balanced on age, health, you name it. But let's be real, reality is messy. We're usually stuck with observational data, where people get treatments for all kinds of reasons, and the groups can be wildly different right from the start.
And this leads us to our number one enemy, a little thing called confounding. So, picture this. You're testing a new heart medication. It's pretty likely that the people who choose to take it are the ones who are already sicker, right? So if that group ends up having worse outcomes, was it because the drug is bad? Or was it because they were just sicker to begin with? It's impossible to tell. That right there, that's confounding, and it completely messes up our results. So, how do we fight back against this confounding beast? Well, we've got to find a way to create our own fair comparison.
Well, the solution is this really cool idea called matching. If we can't use randomness to create two identical groups, hey, we'll just build them ourselves. The core idea is this. For every single person who got the treatment, we're going to dive into a big pool of people who didn't get it and find their statistical twin, someone who looks as similar as possible on all the important stuff.
And this quote just nails it. The whole point of matching is to try and make our messy observational study look and feel a lot more like one of those clean, perfect randomized trials. We're using some statistical cleverness to mimic what pure chance does for us in an ideal experiment.
All right, that sounds great in theory, right? But how do we actually find these statistical twins in the real world?
Well, the most straightforward way is called greedy matching, and it's pretty much exactly what it sounds like. First, you take one person from your treatment group. Then, you scan through all the people in the control group and find the single best match, the one who's most similar. You pair them up, pull that control person out of the pool so they can't be used again, and then you just repeat the process for the next person. Simple, right?
But okay, here's where it gets tricky. What happens when you're not just matching on one or two things? I'm talking about dozens of variables at the same time. Age, sex, blood pressure, cholesterol, their entire medical history. I mean, trying to find an exact match on all of that is pretty much impossible.
And this is where a super clever tool comes into play, the propensity score. Instead of trying to juggle 20 different things at once, we can basically boil all that information down into a single number. This score, from 0 to 1, just tells us how likely someone was to get the treatment based on all their characteristics. So now, instead of matching on dozens of things, we just have to find two people with a similar propensity score. So much easier.
And of course, we've got some quality control measures. One of them is called a caliper. Just think of it like a simple rule that says, hey, I'm only going to accept a match if these two are really close. If the best possible match is still kind of far off, we just say no thanks and don't make the pair at all. It's all about preventing bad matches.
All right, so we've run our fancy matching algorithm, we've got our pairs, we're done, right? Nope, not even close. Now comes maybe the most important step of all.
We have to stop and ask ourselves, did it actually work? You can't just assume it did. You have to prove that you successfully created two balanced groups. Seriously, the step isn't optional. The credibility of your entire study depends on it. And this is the payoff. Take a look at this table from a real study. See that column, standardized difference? That's our imbalance score. As a rule of thumb, you want that number to be below 0.1. Now, look before matching. Mean blood pressure and the neurodiagnosis. Huge differences of 0.35. That's bad. That's some serious confounding. But after we did our matching, bam! They dropped down to 0.01 and 0.02. We did it. We've achieved balance.
And this chart just makes it crystal clear, right? For mean blood pressure, we took this massive imbalance of 0.35 and we just squashed it all the way down to a tiny 0.01. This is just a visual confirmation that our statistical twins really are, well, twins.
Okay, so we've done the heavy lifting. We built our fair groups, we proved they're balanced. So, what now?
Well, the amazing thing is the final analysis is now super simple.
because we took care of all that confounding stuff up front at the design stage, we can just compare the outcomes between our two groups. We can do it with confidence, just like we would have in that perfect randomized trial.
And once we have our matched pairs, we use special statistical tests that are designed specifically for this kind of twin data. The main thing to know is that these tests properly account for the fact that we've created these pairs, which gives us a really solid and accurate answer. So, what was the final verdict in that study? Well, after all that work, the estimated causal risk difference in death was a positive 0.045. Now, what does that mean? It means that after making a fair comparison, the treatment was actually associated with a 4.5 percentage point higher risk of death. That's a pretty big deal.
Okay, so let's boil this all down. What are the big things to remember? 1. Randomized trials are the best, but a lot of the time they're just not possible. 2. Matching is our next best option. It creates statistical twins to make our comparisons fair. 3. Its main job is to crush bias by balancing all those pesky confounding variables. And finally, the most important rule of all. Always, always check your balance to make sure the whole thing actually worked.
So matching is without a doubt a super powerful tool. It lets us find answers in data that's, messy and from the real world. It lets us get close to an experiment when we can't actually run one. But it does leave us with one last nagging question. What about the things we didn't measure? What hidden factors can even the best statistical twin not account for? And that, my friends, is the kind of challenge that keeps statisticians up at night.